All right. Hey, the time has come now to talk about something amazing, okay? And that's something called electromagnetic induction. So we're going to take a look at that here. First, let me talk to you about kind of where we're at right now with electricity and magnetism. So at the moment, we have kind of four big equations that describe how electric and magnetic fields work. Let me run through them really quickly. The first one, you would say, hey, I recognize this one. If I look at the integral over a closed surface of E dot dA, you say, this is a way of measuring the electric flux, right? You say, how many total field lines I have, right? Look at my E field strength. Remember my field strength, that's like field lines per area, how densely packed the field lines are, that's how strong it is. So field lines per area times area, that just gives you field lines. That gives you the flux. And we say, hey, I know if I have a closed surface though, then I know that the total amount of field lines going in are going out minus what goes in, the total flux, that's proportional to how much charge is inside that closed surface. And so you say, hey, this should be proportional to the charge that's inside. The constant of proportionality is this 1 over epsilon naught, right? And that makes it calculate out right. Okay, in this equation we say, hey, that's Gauss's law for electric fields. Okay? If we do this same trick, we have a closed surface, and we count the number of field lines going in and out of that closed surface, but we do it for a magnetic field, then that adds up to 0 always, right? Because you say, and that's the total flux going through the closed surface, but this would be the magnetic flux. I'll put a subscript B, magnetic field lines, because magnetic field lines always make complete loops. And so if it goes out of the bubble in one place, it's going to loop around and come back in another place, right? That's Gauss's law for magnetic fields. We also talked about this idea that if I look at a circuit and I look at measuring my delta V, you see delta V, between one place and another, the change in electric potential, the potential energy per charge, we said that's just going to be integral of E dot, and I wrote it sometimes as dr or d length or ds or whatever. I'm going to write it as dl for the moment. But E field dot dr, that gives me my delta V, right? Well, it's negative, integral E dot dl along that path. Now, something that we talked about is in a circuit, if you look at a complete loop and you end up back where you started, the change in potential energy per charge, right? Delta UE per Q. My change in potential energy, if I end up back where I started, that should be 0, right? And so if I have a closed path, then this is going to be 0, right? This is just like my definition of voltage. If I did a closed loop, I never wrote it like this in class before yet, I don't think, that if I do a closed path, it's going to be 0. But we talked about this as delta V loop. We call that Kirchhoff's loop law. But this is going to work not just in a wire, but any closed path. You end up where you started, the delta V should be 0. All right? On the other hand, if we do a path integral over a closed path, but for magnetic fields, well, then that actually adds up to something, right? Magnetic field lines can make a complete loop, and if you go along that loop and end back where you started, it's going to add to something. And it turns out that it's proportional to the current that goes through that path, right? I sometimes use this. I think about having a wire and having this think about if this is my path, then I think about there being like a membrane that encloses the path, and any current that punches through the path is going to be proportional to this. The constant proportionality we're going to put there is a mu naught. Right? And this, of course, we call Ampere's law, right? So here's the deal. These four equations, then, are going to describe what electric and magnetic fields do if you have constant fields. Okay, so as time goes on, the field's staying the same. For a constant electric field, magnetic field, constant electric field, constant magnetic field. If I do integrals over a closed surface area, right? Over a closed surface area, or if I do integrals over a closed path, right? This is what you get. And it's interesting, right? Look at these equations. Same structure, field strength dotted with the surface area, right, over a closed surface, field strength over closed surface. With the electric, it adds up to something that depends on what's inside. With magnetic, it gives you 0. Integral of a closed path, for electric, it adds up to 0. For magnetic, it adds into something that depends on what goes through that path. Right? Times a constant, right? You see, there's like a symmetry here, right? You kind of see this balance between the formulas, right? Surface area, closed path, something depending on what's inside, 0, 0, something depending on what goes in through. Isn't that kind of neat? the person who first looked at this and kind of combined all this together and noticed this, his name was James Clerk Maxwell. This is what the Maxwell equations look like, or one way of writing them, for systems that have constant electric and magnetic fields. Kind of neat how it all kind of balances out in this nice, beautiful symmetry. This is very pleasing, like aesthetically pleasing. But it turns out there's something else going on here that's different. That's going to cause this symmetry to kind of break and kind of screw up the beauty of Maxwell's equations. All right? And so that's what I want to share with you today. It's electromagnetic induction. And then I want to share with you how Maxwell fixed that and got it to be symmetric and beautiful again. All right? Kind of neat. So here we go. So let's start with this. And that's so now I'm going to move on to today's topic. So first, let's talk about the fact that if I have a wire and I run electric current down a wire, then we know that those moving charges make a magnetic field around the wire. This was first noticed by this guy named Ørsted, Hans Christian Ørsted. And he says that he first noticed it during a lecture to his students, but anyway. The point is that we know the magnetic fields go in loops around the wire. How do I figure out the direction of the field lines? You take your right hand, you grab the wire with your thumb pointing the direction of the current. So if the current's going to the right, I would grab the wire like this with my thumb pointing to the right. The way my fingers naturally loop around, that's the way the field lines loop around the wire. Moving charges make a magnetic field. All good, right? And when they first found this, you could find if we're running current down a wire, it's going to make compass needles turn to face along the field lines right around the wire. There's like a little experiment that students can do where you take a little wire and you run current through it and you kind of move a compass needle like around the wire and make sure that the field line's always going tangent, right? The compass needle will point tangent to the field. They'll make little loops around the wire, right? You can kind of map out the field and you get it. Well, trying to figure out like why this happened and like how exactly it worked. The electric charges moving made magnetic fields, right? This is a task that got basically given to Michael Faraday. Right? That's the guy who first thought up electric field lines and magnetic field lines and doing these diagrams, right? And so he kind of had to come up with an explanation for it. And so he tinkered with this for years, right? Looking at this stuff and trying different combinations of wires and coils and turning current on and changing things. And he finally figured out a way of describing what I'm going to show you in a minute, okay? So again, Michael Faraday's the guy who first figures this out. Let me show you. To kind of explain and kind of show you how it works, I'm going to use a certain device. I got to show you how this device works. Now, this is going to harken back to something we talked about before. Remember we talked about the fact that if maybe I set up this little setup where maybe I have a great big magnet, North Pole, great big magnet, South Pole, the magnetic field lines will go out the North Pole of one magnet into the South Pole the other, right? Out the North in the South, that's the way they go. I like to do my magnetic field lines in purple, but sadly, that purple pen is out of ink. I'm going to open a fresh box, right? And hopefully I'll have lots of good juicy markers here. Here we go. So, please work. Okay, there we go. The magnetic field lines would go across. Remember we did this? And we talked about the fact that if I took a wire, like a loop of wire like this, right? And we said, hey, if I hook this up to voltage, so I had a high voltage side, a low voltage side, right? Red, black, can you tell? Right? Then my current would go from high V to low V. It would go around in this loop. See? A little arrow. Says current's going to the right. Anyway, if I stuck this in that field, so we talked about how the wires would get yanked on each side, yeah? As the current goes in here, V cross B, force would be down. And on this side, current coming out towards you, and we did V cross into B, force would be up. This side would get yanked up, this side gets pushed up down, and makes this want to rotate. And we talked about how if I flip the direction of the current every half turn, then I could get this to spin and spin and spin and spin, and I have an electric motor, right? But we're going to make a little change to this, okay? I'm going to set up my coil, right, like this, right? And I've got my inputs here that I can hook up a voltage to, right? But what I'm going to do is I'm going to attach springs to each side of the coil. So if this thing wants to tilt, it has to stretch springs. So if I run current through, it'll start to tilt and it'll stretch springs on one side and compress on the other, whatever, right? It'll stretch the springs, right? And the more current I run through, or the higher voltage I hook it up to, the more current I would get. The harder, the bigger the torque, the twist I'll get, the more current, the bigger twist, and it'll stretch the springs further. If I run current the other direction, then this will get yanked down, and that'll get yanked up, and it'll go the other way, right? Do you know what I've just made? A device that can show how much current or how big of a voltage I got hooked up to this thing. But imagine I put a little indicator arrow here. I run the current one way, it tilts one way. I run the current the other way, it tries to go the other way, right? And so by how far this thing tilts, I can register what my voltage is I hook this up to, or what current I'm running through. Neat, huh? That device is called a galvanometer, right? Named after Galvani. Galvanometer, right? Luigi Galvani. That's the guy who was playing around with frog legs and looking at how current running through frog's legs made those muscles twitch. But anyway, the point is, that device is this device. Here is a ginormous galvanometer, an old-timey galvanometer, right? It says galvanometer here, and then it says volt-ammeter, okay? Because it can measure voltage or current, if you know what the voltage, right? Now, inside in there, and I know you can't tell very well, but right in there, that's where that coil is, right? This loop of wire, but I run it around like a bunch of times so I get a big force on it, right? It's a little kind of copper coil right in the middle there, it's actually oriented this way, because my magnets are above and below inside there, instead of side to side. But that's the idea, okay? And here's my little needle attached to it that'll show, right? What do you think? All right, galvanometer, that's how it works. This thing is not, I mean, look, it's not plugged into anything, okay? This is how it works. That's what powers it. Now, here are where I would wire in my current, right? The current, the voltage I want to test would hook up there, one side, other side, right? To make this thing twist, to tilt the needle. But look what I've done. I've got a wire that goes from the input around to the output. There is no voltage source, there's no battery, there's nothing hooked up to this wire, and so you're not surprised that it's not registering any current or any voltage, right? Absolutely. All right, that's the deal. Until I start playing around with a magnet. All right? Now, for my demonstration here, I'm going to start with this. Okay? This, can you tell? It's like a coil of red enameled wire. So there's a wire here, copper wire, but it's got this red enamel, so it's not it's an insulating surface, that enamel, so the coils of wire can't touch each other without, shorting out. But this is a coil wire that goes round, 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 round. I've got places where I can attach, hook up on each end, right? And I can run current through this coil. This is a solenoid, right? This helical winding of wire wraps around and around, 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 around. Okay, so I can hook it up to a battery. Here we go. I could just click one end, right? And here I've got a pile of steel paper clips, right? So you say, hey, if I go ahead and I complete this circuit, then current will run through. It'll make a strong magnetic field that will shoot down the coil, right? Here we go. If I click this, right? And you say, wait. Can I indicate that somehow? You say, well, of course I can indicate it. I could use a compass, right? Compass needles, of course, are little magnets and they'll show magnetic fields. So I'm just going to go ahead, set my compass down there. You can see a little compass needle, the north end pointing this way, right? Yeah. Okay. Here we go. Set that nearby. 3, 2, 1, click. You see the compass needle swing. Goes back. Swings back, goes back. I'm making a magnetic field and the field lines loop out and go around, yeah? They're coming in, curving in like this. If I move it over here, it's got to swing a little further, but you get the idea, right? Okay, making a little magnetic field. Everybody's happy, right? Okay, so if I go ahead and I turn this on, can I pick up paper clips? And you say, no, right? Here's the deal. I want to make that magnetic field stronger. You say, I remember that we derived a formula for the magnetic field in a solenoid. It looked like this. B is mu naught Ni, where this is my loops per meter. There's a bunch of little loops. Loop, 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 loop. This wire goes round, 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 round. I mean, here, bring it closer to the camera, if it'll focus. And there's coils on top of coils there, all right? So there's layers here. It's like a whole bunch of loops per meter, right? Tons of them, right? I'm gonna run some current through. Well, whatever this 6-volt battery can provide, right? Depends on the resistance in the wire in the solenoid, right? Okay. And this constant, oh, wait a minute, what's this constant? That's 4 pi times 10 to the negative 7 for empty space. And for air, it's about the same thing. If I put a different material in there, a different core in that solenoid, I'll increase the magnetic field strength. So here we go. I'm going to go ahead and I'm going to take this chunk of iron, okay, this little iron bar, and I'm going to slip that in here, all right, and we'll see what difference it makes. Here we go. Attach. Let me attach. Again, I can verify. Whoops. Here, detach. Here's my little compass needle. Verify that I'm making a field. See the compass needle swing? Yeah. Okay. Bring it near the paper clips. Nothing, right? But what if I put an iron core? Sliding the iron core in. You see that compass needle respond. Look at that. Work, 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 right? Okay. Bring it near. And now I'm in business, right? And pick up paper clips. Turn off the electromagnet, break the current. All right, paper clips fall. All right, what do you think? All good? So, here's what we're gonna do. All right. So that's a little bit with the solenoid. I'm gonna show you some more with the solenoid in just a minute, okay? All right, I'm gonna show you the easy way first. Here, I have a magnet, okay? This side, you might notice, I've tagged N for North Pole. The other side, which I didn't tag, is the South Pole of the magnet. So field lines are going out the north, looping around, coming in the south, okay? Out the North Pole, loop around, come in the South Pole. Okay, now, here we go. Here is my wire. It turns out that if I use a magnetic field, I can go ahead and I can push on charges, right? If the charges are moving across the field lines, right? That's what we've been told, yeah? That's the Lenz force and all that. Can I use the magnetic field to make charge flow in the wire? Then it would register on the galvanometer, right? Yeah? So here we go. Here is my wire, right? Check this out. Okay, I got the wire. I'm gonna move the magnet to the wire. Do you notice that little needle move in the galvanometer? You're like, Mr. C, what are you talking about? There's nothing going on there, right? Is this making charge run on the wire? You say, no, nothing that can detect. However, what if you notice how I was doing this, right? I've got that wire in a loop, and I'm going like this, and we're not seeing what's happening. On the other hand, if I turn the magnet like this, right? And now I go like this. How about the other way? You're like, I'm still not seeing much, Mr. C. Try this. Here, sorry. Hold that so you can see it. Can you tell the needle is twitching a little bit? You can see that, can't you? But when I go this way, needle's not doing anything. Do it this way. You're like, huh. I'm making that needle move, and I don't have this hooked up to any current, any voltage at all. Somehow, moving this magnet is making current run in this wire and trigger that and tug on that little galvanometer. And you say, hey, clearly it's something with the magnetic field. It's something, it doesn't happen if the magnet's just sitting still. Nothing going on. It happens when this is moving. Or, what if I hold the magnet still and I move the wire? Drunk, shunk, shunk, shunk. Can you tell, you can see the needle twitch? One way, other way. Little twitches, right? Okay, here we go. We're gonna do something different now. To make this work better, it'll be a little more obvious. If one loop of wire is good, maybe, or actually better yet, before I do that, I'm just gonna cheat. I'm gonna scale this up to a more powerful magnet. Here, I have a ginormous magnet, okay? Okay, and one side's got this little residue of tape on it. That's the side that's the North Pole. Here's the South Pole. This is a ginormous magnet, okay? How can I show you this magnet's ginormous? Okay, all right, here, look. It's not falling off, right? Right. You're like, hey, this is a really strong magnet. Okay, so try it this way. Here's this loop of wire, right? Okay. Okay, here I am, moving that magnet. Is the needle twitching? Hardly anything. Now I'm going to rotate the loop like this. Get my arm out of the way. Ready? Bring this near. Shunk, 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 shunk. Right? You can see the current flow one way, other way, one way, other way in that wire. Now, if one loop of wire is good, shoop, shoop, shoop. Let's loop that around 3 times. Ready? Check this out. Shoom, shoom, shoom. Look at that. Now, watch this. Doing it in slow motion. See much going on there with the needle? Yeah. In slow motion, going away. Gets tugged the other way, right? What if I go quicker? Shunk, shunk. Interesting, huh? What is making the current flow in the wire? Right? How do you describe this? What exactly do I have to do? If I have the coils like this, oriented this way, and I move the magnet like this, right? Look at this. Very little, right? Like this, shoom, 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 right? What if I'm off to the side of the coil? Very little. Now the coil, shoom, shoom, shoom. Look at that. Here's the deal. What I want you to remember is the magnetic field lines are going out the north pole of the magnet, and they kind of spread out and they curve around and come back in the south side, right? So here's my field lines. There's my fingers, right? Kind of coming out and spreading out. If I'm holding the loop like this, some of the field lines, remember they curve, are going to miss the loop. Some of them will go through the loop, but some of them will miss, go one side or the other side as they spread out. If I push this closer, right, I'm going to have more field lines going through the loop. And if I move farther away, I'll have less and less field lines because some of them will now curve to the side and miss. Can you picture that? Anything I do that changes how many field lines go, magnetic field lines go through this loop of wire, of conductor, will make a voltage and push charges down that wire. Okay? I can change how many field lines go through by moving the magnet closer or farther, right? Notice that if I go one way, the current pushes one direction. I go the other way, the current gets pushed the other direction. We'll have to talk about that, which direction the current goes. That's something called Lenz's law. We'll get to that. But you say, anything I do here that changes the field line, I can do this by making the magnet closer, farther. I could do it by moving the wire loop closer, farther. Yeah? I could do this by rotating the loop. And that'll change the field lines going one way, other way, through that coil of wire, yeah? Okay, that would work. I can do this same trick with the electromagnet, with the solenoid here, right? I can go ahead, I'll put my iron core so I get a stronger one. All right, here I have my loops of wire. I'm going to push this. Look at this. If I turn this on, if I make the connection, suddenly magnetic field lines will get generated by the current going through that coil, and field lines will go shooting through this iron bar and shoot out one end and loop around and come in the other end, right? Here we go. Watching. 3, 2, 1. Click. You know what? One way. break connection, needle twist the other way. Make connection, break connection. Make connection, break connection. Anything that changes how many field lines are shooting through this, and the field lines can be going through like the metal bar here. They don't have to be going through empty space, right? They don't have to be touching the wire at all, the field lines. It's just the field lines going through this path, this loop of conductor. The person who figured this out, of course, was Michael Faraday, right? The guy who first thought of field lines and doing these diagrams of field lines, figured out that this is the trick. Now, it turns out, I'm going to tilt back up, there's a couple ways of describing how this works. I'm showing you right now the way that works every time, okay? It's looking at how many field lines go through that closed path. And if you change how many field lines go through the magnetic field lines go through that closed path of conductor, you will make a voltage in that conducting wire and will push charges around, make a current, okay? That's the way it works. Let's put that now in like math speak, okay? Let's put that in symbols, all right? Symbolically, if I change the number of field lines, right? Oh, sorry. The other thing that matters is how quickly we change the number of field lines, right? We saw that if I had that coil, right? If I have that loop, and I have my magnetic field, we said if I move it quickly, shoom, shoom, it makes big current flow, right? Big voltage making big current flow. If I do it really super slow, slow change in field lines, hardly anything registering at all, until I bump it and make it quick, right? Go quick and shoom, right? Slow, hardly anything happening there. Slow, hardly anything happening there. Go quick, shunk. Go quick, shunk, right? Okay, good enough. So what matters is not just the fact that we're changing the number of field lines. What matters is how quickly we're changing the number of field lines. In other words, the rate of change of, what do you call the number of field lines? The flux. The rate of change of magnetic flux through that loop of conductor makes a voltage that goes around that loop. So here we go. If I had a rate of change, ddt, of magnetic flux will generate then a voltage. And you say, okay, now wait, so that would be like a delta V, right? But when I make that delta V, you say, wait, we have an equation for delta V going around a loop. It's this. That means I'm making an electric field in the wire when I change my magnetic flux through that closed path. What happened here? This equation was only for constant B fields. If I have a changing magnetic flux, magnetic field strength changing and I'm moving stuff around, then I'm going to make a voltage in the wire by that. And it's going to make an E field. And this loop will not add to 0. Okay? So this is a modified form of this that works if I've got a changing magnetic field. You say, but wait a minute. We had this beautiful symmetry between the 4 Maxwell equations, right? The 4, and you say, there was this great symmetry with this and 0 and 0 and that, right? And it was really neat. But now, when I add this term in, that's not 0 anymore. If I got changing flux, I got this d phi v dt, right? Oh, by the way, yeah. And so that kind of like messes it all up. Okay, one more thing. I just realized there's one more thing I want to put in the equation for you. And that is, you remember the other thing that we did with this wire that gave us a bigger effect? And that was, instead of having one loop of wire, we like wrapped it around, made a coil. So I might want to have an N here for the number of loops of the coil. Okay, all right. Yep. Okay, so anyway, what do you call this equation that we just wrote here? Oh, but one more thing. This is a delta V, right? Here is a loop of conductor, right? Loop of wire, right? What I'm going to do is I'm going to take a bar magnet. Let's say that I'm going to move that magnet this way. It's got a velocity that way, towards the loop, towards the wire. Now, I got to try to make this a perspective picture, because I'm just showing magnetic field lines. There'll be magnetic field lines shooting. This is the dead marker again. The magnetic field lines shooting out of the north pole of that magnet, right? Through the magnet. They're going to go in front. I'm going to draw this thicker. They're going to go in front of this side. And then out there, right? This is like the near side of the loop. That's the far side of the loop. See? That's behind the magnetic field line. This is in front of the magnetic field line. Does that make sense? Okay. So here comes my magnetic field lines. Right? And I'll have some field lines that'll miss the loop, right? So if I move this closer, these ones that are missing will then end up going through the loop. So I'm changing how many field lines go through the loop. They're changing the flux through that loop of wire. And that will make a voltage that'll make current run around in the wire. Okay? I'm not going to tell you which way it runs. There's a specific way that it runs. I'm going to show you that rule in a minute. I want you to logic through which way it has to go. But it's going to make a voltage in that. Now, here's the problem. I'm making a current, right? This is a wire. It's got some resistance to it, right? Every wire's got some resistance, yeah? Okay, which is rho L over. Anyway, the point is, you say, I'm making a voltage, there's a resistance, there's going to be a current that flows, right? And the current I can show in the magnetometer, right, or galvanometer, right, and everything's fine. Here's the problem. We're talking about making a voltage that makes a current flow. Voltage means there's a delta V. That's like a V final minus V initial from one spot to another spot. What are the two locations on this coil, this loop that we're talking about? We're talking about the change in energy per charge, V is UE per Q, going from here to here. That's what we're talking about when you go all the way around the loop. And you're like, Mr. C, what are you talking about? If I end up back in the same spot, that total delta V had better be zero, right? What's happening here? Why is there actually going to be a change in UE when I go around and end up where I started? Here's the way I want you to think about it, okay? 1 second. I'm going to do an analogy here. It will be even better. There we go. Even better with that. Okay. Ready? Consider this. What I want to do is I want to talk about the fact that delta V is the delta UE per Q, electric potential energy per charge. I'm going to do an analogy for you, okay, with gravitational potential energy. All right? Let's say that I have a little path on this surface. Okay? What I'm going to do is I'm going to roll my ball around on that path. As it goes this way, it's losing height, so it's losing gravitational potential energy. And it comes this way, I would have to gain gravitational potential energy. Maybe I have like a little lip, like I put a little hoop down on here, and as it rolls around in the hoop, it picks up speed, kinetic energy, and then it makes it roll back up and gains potential energy again, and then loses potential, gains kinetic. It would go around and around. In a complete loop, the change in potential energy would be 0. But what if I do this experiment while I'm going down in an elevator? Maybe I'm accelerating down. If it goes around in a path, and it ends up back where it started, it's not really where it started. It's lost gravitational potential energy. So it's actually going to end up moving faster than it did when it started. Can you picture that? Every time it goes around, we're losing gravity. The elevator goes down, 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 down. It's going faster and faster, right? As it gains kinetic energy, because we're losing gravity. Where else is that gravitational energy going to go for that ball as it goes down? It's got to go into kinetic. It's going to whip around faster and faster in that track. in that tilted track. Do you see that? Weird, huh? That's like what's happening here. Going around this path that you'd think you'd end up back where you started. The change of potential energy would be zero. But the situation is different. It's not the same as it was the last time the electron was there, because the magnetic field strength is changing, because this is moving. And so it's a different situation by the time it gets back. And it's a different potential energy now, and that's the deal. Neat, huh? So this is what messes with people's heads. If you think about delta V, going from one spot back to the same spot, shouldn't that be zero? But like I said, it's not the same situation as it was, because the magnet has now moved, right? You know what I mean? And so what they do sometimes to kind of hide that confusion, kind of make it easier for them to think, is they'll use a different symbol here for delta V. Because we're going from the same, because always someone looks at it, well, from where to where? Or from the same spot to the same spot, and they're like, wait, shouldn't that be zero? And to keep people from having to ask that question all the time, instead of using that symbol, they'll use this symbol, the electromotive force symbol, the EMF. What does it mean? It means delta V, all right? But it keeps people from asking this question about from where to where, and from same spot to same spot, and they're going, huh? Right? So we use this. You've also seen me use this symbol on batteries to talk about the ideal voltage of a battery between the two terminals of a battery, right? The open circuit voltage of the terminal voltage of a battery, open circuit. We use this symbol, EMF. All right. So there you go. Okay, so this equation then, okay? A lot of times I'll see it written, like, where's the AP formula sheet here? Yeah. So if I look at the AP formula sheet, they'll write it as EMF equals, right? And then they'll write it as integral E dot dl, right? And then what they do is they take the negative sign here, which we know from that formula, and they shove it over here onto this term, like that. And they use the EMF symbol instead of the delta V symbol. Okay? They have these two terms flip-flop, but it's the same thing, right? That's the way the formula looks on the AP sheet. What we call this now, because the guy who first figured this out, that changing the number of magnetic field lines through that loop of conductor, right? Changing the amount of flux, the magnetic field lines going through, will make a voltage. That was Michael Faraday who figured that out. So this is now called Faraday's law of electromagnetic induction. Because that's what we call this, okay? We're using changing magnetic flux to cause charges to flow, to cause a voltage. We're inducing a voltage in the wire by changing the magnetic flux through that closed path of conductor, okay? And that's it. That's Faraday's law of electromagnetic induction. Now, when you look at this, you say, that screws up the whole symmetry of the four equations. If I take this guy, and I make this EMF as negative, just now you kind of screwed that up. Faraday figured out, James Clerk Maxwell, looking at the four equations then, said, you know, that throws everything off balance. There needs to be something else here to kind of repair that symmetry that's been broken, right? And he figures out one of these other equations is going to change if I have changing magnetic field strength. You say, well, changing magnetic field strength will make an E field. Maybe if I can change, or like changing magnetic flux, maybe if I have a changing electric flux, that will affect the B field strength. That's exactly what happens. And he modifies this equation to include that. Should I show you what the equation looks like, or should I run through the whole derivation? I'm just going to show you what it looks like for right now. So he's going to modify Maxwell, looking at the equations, trying to sum up all the electricity magnetism equations, sees the symmetry get broken when we have changing magnetic flux. So he said, hey, there's going to be another term here, right? And that's going to deal with changing electric flux. All right? So there'll be a d phi dt, right? And there'll be epsilon naught there. Wait, I think there's a mu naught epsilon naught actually, now that I think about it. There's a mu naught epsilon naught d phi e dt. So this is going to take some explaining to talk about where this comes from. let me just double check that I've written that properly. I don't want to go too much further here without with giving you the wrong Maxwell equation. That would be bad. Right? That would be annoying. Give me a second here. Yeah, of course that's right. Okay, so yeah, so we tack on this term, and that's the fix. When you do this, this was Ampere's law, right? Now it's called the Ampere-Maxwell law. When you include this term that was missing, okay, that Maxwell figured out. And so we have this term with changing flux making magnetic field. Like here we have changing magnetic flux making electric field. Neat, huh? And again, it's symmetric again, the four equations. Okay, these of course are Gauss's law for electric fields, Gauss's law for magnetic fields. Those are the four, the four equations of electromagnetism. Okay, the Maxwell laws. Okay, so changing electric flux can act. See how this is like mu naught times the current that goes through my path? This is like mu naught times this going through my path. Changing electric flux going through my path. Okay, and that acts like a current to make magnetic field. This is actually called the displacement current, but that's not important. Okay, good enough, all right, for right now. So we can make charge flow in wires if I've got like a closed path of conductor by changing the magnetic field lines going through that path. Anything we do to change the magnetic field lines going through that path, changing the angle the field is going, changing the strength of the field, changing, if I've got a source of the field, moving it closer or farther away, changing the angle of the coil, right? You know, anything you do, moving it sideways, that changes how many field lines go through that path will make, that changes the flux, the total number of magnetic field lines going through the path, will make a voltage run around in the conductor that way. Okay, and that's called electromagnetic induction. Okay, that's it. What I should do at this point is I want to talk to you about how do you know which way the current will flow around in that loop. Right? So I'm going to draw this sketch. I'm going to draw it again a couple ways here and talk to you about how that has to work. All right? How that has to work. Let's say here I have my loop of wire. This is the front, the near side, and this is the back side, okay, the far side, okay? All right? I'm going to take a bar magnet, North Pole, South Pole, and I'm going to move it up towards the loop. This is like the diagram I did there. I just rotated it 90 degrees. Okay? This is going to make magnetic field lines shoot up through the loop like that, yeah? Agreed? Yeah, that's what it looks like. Okay? All right. Some of these field lines will miss the loop, right? So by moving it closer, these ones will now go through. They didn't. What I'm doing is I'm changing the amount of magnetic flux, the number of magnetic field lines going through the loop, that will make a voltage in the wire, that will make current flow around in the wire, right? Here's the question. Which way that current that we make flow, that we cause to flow, that we induce to flow, is called the induced current, okay? The question now is, in this picture, it's kind of looking slightly down on that loop. Is the induced current going to go this way? I induced, question mark. Or will the induced current go around this way? I induced, question mark. Here's the way, I'm going to explain to you why it has to work the way it works. The rule that tells you which way it goes is called Lenz's law. All right. I'm going to write that over here. Okay. L-E-N-Z. Okay. Apostrophe S. Lenz's law. Okay. That's what I'm going to show you now. Okay. Let's figure out how it has to work. If I run current around in this loop now, wait, what happens if I have moving charges in the loop, right? Okay. We say, hey, let's guess. Let's make a guess which way the current flows. We're going to guess that it goes clockwise as I look down on this loop. We're going to guess that it goes counterclockwise as I look down on this loop. For our purposes of our discussion, let's guess that it goes counterclockwise. Let's guess that this is right. If that's right, you say, well, then if this makes current flow around, wait a minute, the current flowing in the loop, won't it make its own magnetic field? Here's that loop. If the induced current goes around this way, it'll make its own magnetic field. What will that magnetic field look like? Well, this is where I use my right-hand rule. I'll grab the wire with my right hand with my thumb in the direction of the current. If the current's going to the right in front and to the left in back, I grab the wire like this, thumb in the direction of the current. And when my fingers loop around the wire, that's what the B field lines would curl on the wire. That means this will make a field that shoots up through the middle. Yeah, of that loop. As it goes around, it'll be going up all the way around. So this would make a field of its own going this way, right? Like over here, the way we drew this, right here, the current is going away from you, right? I would draw an X there. That current is going away from you into the page. Over here, I draw a dot. That current's going out of the page towards you, right? So the field lines, grab the wire from the direction of the current, it would loop around like this. Field lines would loop around like this. Yeah? And over here, field lines are looping around like this. We're good, yeah? Okay. Now you ready? Here's how we figure out. Let's imagine that we're moving this magnet closer and closer. We're increasing the flux up. The magnetic field, all field lines, the flux up is increasing. Okay? If that makes the current run around this way, you say, wait a minute. This guy makes his own field. You see field lines are going in on this side and out on the top? In on the bottom, that means this is like a magnetic south pole, and this is like a magnetic north pole, isn't it? Do you see that? This is a little electromagnet, makes its own field, yeah? So hang on. If I move the north pole of this magnet closer, and that makes the charges flow around this way, they would make their own south pole here. What would that do to this north pole? It would pull it in faster. And because how quickly we change tells us how big of a voltage we make, which tells us how much current we make, which tells us how big this field is. If I push this in and it makes the current go that way, this makes a B field that attracts in and makes it go even faster, which would induce a bigger voltage and make even more current flow around, which makes a stronger field to pull it even faster. And so if I go ahead and I put this here and I give it a little nudge, then it would get pull, faster, and I get zzz, all this energy coming out for free. And you're like, no way. The universe does not work that way. Right? I can't just give this little nudge, all of a sudden it gets yanked up and like all this current, all this energy being produced. Which way does the induced current go? It goes the other way. My induced current has to go this way. And so the magnetic field lines will go the other way. And this will be the magnetic north, and this will be the magnetic south of our induced magnetic field here, right? In my field lines, current comes out, field lines loop around like this, current goes in, field lines loop around like this. Yeah? So, here's what happens. My induced current is going around this way, right? Going around this way. Yeah? That induced current. This is the induced magnetic field that was made by the induced current. So, not this one, this one. So, as I push this north pole in, right, that's going to shove on the electrons, make the electrons move, right? It's like I'm giving those electrons kinetic energy, right? Making them move. right? Where is that energy coming from? It's got to be coming from me, right? As I push this then, is it free for me to push that in? No, because when they move, they make a north pole to fight against me and repel. So for me to push that there, I have to do work. Do you see that? I have to apply force through a distance. Where's that work going? To pushing the electrons through that wire, right? Okay, and making them, if this is part of a circuit, maybe there's light bulbs and stuff, as the charges go through, they'll push through that and the resistance, and they'll burn off that energy as light, right? Okay, light bulbs, heat and light. Okay, so I can use that energy to power different things from me moving this. That's how it works, all right? So, Lenz's law. I'm now going to tell you what Lenz's law says. Lenz's law says that the induced current, or the induced voltage, is such that it creates a current whose magnetic field opposes the change in flux that made that voltage happen in the first place. Yeah, I know. When you see it written out, it's confusing. Essentially, what I'm saying is, it always is going to try to fight against what you're doing, fight against the change. So watch this. As I push this closer, what happens to the magnetic flux through this loop? There's an increase in flux up through the loop. What's that going to cause? It's going to make current flow to make an increase in flux going down through the loop, to fight against the change. That's the way it always works. Okay? So my cause, the effect, current flows to increase the flux going down. It always, through the loop, it always tries to fight against the change, okay, to maintain the status quo, what it had before. Okay? That's the idea. That's what Lenz's law is about. You know, we have this equation. This negative sign is meant to kind of indicate Lenz's law, that the voltage acts opposite, to make a change in flux that's opposite the change in flux that made it flow. Does that kind of make sense? Hope that makes sense. Okay, this is it. This is the idea of electromagnetic induction. There are so many cool applications and stuff to talk about with this. But yeah, that's the way it works. That's enough for one video, though. I need to cut this video off so it's not too long. So I hope that you're okay with this. If you've got questions, don't hesitate to email or ask me, okay? I'm happy to talk about it. I will try to put out a few more videos with demonstrations. MECU, Mechanical Universe, has a great episode on this that you should, of course, take a look at. Okay, there's another explanation for how induction works, and I want to show you that with another example in the next one.